Hey! Do you know what these books, these rows,
this paragalaxy and this picture have in common?
they are all beautiful examples of how mathematics is all around us, and how a simple number can be expression of beauty and harmony. The number I want to talk about is called phi. Its symbol is the Greek letter phi. Phi is an irrational number. Irrational numbers are those numbers like some radicals or everyone's friend pi, whose decimals are infinite, and there's no repeating pattern among them, and they go on and on. And guess what can come from an irrational number? Another irrational number. And now we'll see how and why.
Let's first talk about the special ratio obtained when in a line divided into parts. The ratio of the total length to the longest part of the line is equal to the ratio of the longest part to the shortest. When this condition is satisfied, we are talking about a golden ratio, and the value of this ratio is phi. To derive phi, we give value x to AC, value 1 to AB, hence BC will have value x minus 1. To satisfy the golden ratio, we get a fairly simple second-grade equation with two solutions, but we only care about the positive one. That is our phi, and it's equal to 1.61803, and it keeps going on and on.
Phi has so many incredibly interesting and mind-blowing properties by itself and related to its closest friend, the Fibonacci series, a series expressed by this. It means that a number in place n in the series is equal to the sum of the two previous numbers. This series is infinite, and these are just some of the first numbers. The particular thing is that every number of the series, divided by its previous one, will give as a result a number that is really close to phi. And the farther you go on the series, the closest the approximation will be, and we are talking about decimals. Unfortunately, in only 5 minutes, there isn't enough time to show you all the properties of phi, so I'll just show you some.
Knowing that that equation is verified for phi, we can rewrite it like that. Then, if we keep multiplying it for phi n times, we will get something that looks like that. And we can already see some similarities with the Fibonacci series. Another property. We get from the starting equation of phi that phi squared is equal to phi plus 1. So we substitute it in the first equation that we found before. Then we keep substituting the results that we get in the following equations, and we will get something that looks like this. Now, if you pay attention to the coefficient of phi and also the other numbers, you'll see that are all parts of the Fibonacci series.
However, more than the number itself, it's important to understand the relation of phi with a lot of things that are all around us, like this book. And for this reason, we need something more concrete than a number. Let's go into geometry. Let's draw a golden rectangle. A golden rectangle is a rectangle where the ratio of the longest side to the shorter side is equal to phi. The golden rectangle is not the only geometrical shape that you can draw with the golden ratio. There are also golden triangles and the regular pentagon that contains phi by itself, and that is just amazing. But let's go back to the golden rectangle. It has amazing properties too.
If we subtract a square from its shorter side, we will get another rectangle that, guess what, is golden too, and we can keep doing this infinity times. Trace two diagonals as shown. They meet each other in a point that is the starting point for the golden spiral, a spiral that passes through the opposite corners of all the square.
And we can find this spiral in nature in more things that we would expect, like in the Nautilus, in the disposition of the seeds of the sunflower, or in some spiral galaxies, and in a lot more things. And this is just amazing. It's just a taste of the expression of phi around us. If the diagonal of the first reaches the corner of the second, we have two golden rectangles. So let's try. As we can see, it works. So these two books are golden rectangles. Let's try with the credit cards. And as we can see, it works this time too. This is not just a case. The golden proportion is used in the industry because it's considered pleasant to our eyes. It's considered expression of beauty and harmony. For this reason, famous artists like Leonardo da Vinci, that was a great mathematician too, were obsessed with the golden ratio, and they studied this proportion a lot, and you can find it in many of their pictures. A great example, the Mona Lisa, and we will see.
For example, the ratio of the height of her head to the width is equal to phi.
This portrait is considered beautiful and full of harmony, and many suggest it's because of the proportion in it. Studies also suggest that a face or a body is more attractive if the proportion in it are close to phi. Crazy, isn't it? Numbers can influence our conception of aesthetical beauty, but don't worry, the real beauty is inside and numbers cannot touch it. Unfortunately, I'm short of time, but there is one last thing that I want to show you that is probably the thing that captured me the most. That thing is the disposition of petals and leaves in some flowers and plants. It's crazy, nature found out a way to dispose them in the most efficient way possible, so that they never overlap each other completely. letting the most light hit the most surface. The angle that makes this possible is 137.5 degrees. And yeah, somebody used this funny tool to measure it.
We have circumference that represents all the possible disposition. B is the arch that is subtended by the angle. We find its ratio to the circumference. We give value 1 to the circumference, and we can find also the ratio of A to the circumference. Then we find the ratio of A to B, and we find that is equal to 5. So, for this reason, it has to be true that also the ratio of the circumference to A is equal to 5. From these two formulas, we derive that B is equal 1 over 5 square of our circumference, and we can check this.